Alright, hey guys. Today there is the Codeforces round 708 Div 2, which I'm a bit late for actually. And yeah, so let's just get into that. I'm going to update the sub count, which I haven't done in an incredibly long time, since I haven't done a screencast in C++ in a while. The last one was Kotlin Heroes. But anyway, I guess we can get into this. As soon as I find my pen. Yes, okay. Maximization. You have an integer and an array. You should reorder them so that the sum of the maxsum prefixes is maximized. Okay. So if you have a 0, you want to put it at the beginning, otherwise it doesn't matter. And okay, sure. So you want to put a 0 at the beginning and then a 1 after the 0 and a 2 afterwards, etc. And if you don't have a 0 to put at the beginning, then no matter what, the max will be 0 everywhere, so it doesn't really matter what you do. So the basic idea is so basically the first element we try to put at position I is I itself. So if count I is greater than 0, AI is equal to I minus count I. Else we means we can't do better because we don't have any more of this element, so we can't get a greater max. Like say the max is 3 and then we don't have a 3, then there's nothing we can do. So it doesn't matter what we do after that point because we can't increase the max anymore. So we can basically just find any element, j equals 0, j is less than 1 or 2, j plus plus. If count j is greater than 0, AI is equal to j, and break. Then, yeah, so we just assign it any element. Multi-tests. Also, I don't think it's enough to sort, but I'm not sure. Oh, that's what? Count I is greater than... Oh, well. That does not make sense. Yeah, okay. I don't know what it was doing there. So technically this will sort of sort the array, but also like not really because it'll try to maximize the max first. Looks like it works. I have Python because I was trying something. Okay, just to make sure the mic is picking up sound. I would hope so. I also hope it's not lagging as much because that used to be what it did before, but who knows. I did mess with a couple settings just to try things, although I'm not sure how effective it was. Okay, anyway, you have an array and a positive integer m. You should divide the elements into this array into some arrays, and you can order them however you want. Let's call an array m divisible if their sum is divisible by m, so the number of residues mod m, I guess. Should be the number of residues mod m. Yeah, because if you have two different residues, then it doesn't work, and if you do, then do we have to print the actual arrays? Good, okay. Okay. So if we have two different residues mod m, then basically we can't put them in the same array because their differences will not be 0 modulo mod m, or it will not be divisible by m, which is the same thing. And if we have two things in the same residue, like say we have m equals 4 and both of them are equal to 2 mod 4, then their difference is going to be divisible by m because their value mod m is the same. So basically it's just the number of distinct values we have. Count x mod m plus plus. mind actually. If this is equal to 0, also stands. To turn off the auto recommendations for Notepad++. Seems like they never actually would do anything. What? Oh. Okay, that was arguably. Oh, what? 1, 2, 5, 8, 6. Oh, there's some. Okay, that makes more sense. Okay, misreading the problem. Awesome. That's a good start. Perhaps there is a different way to think about it. If we instead, like, suppose that like m equals 6 or something, then when we have something that's 2 mod m, we have to pair it with something that's 4, and then we have to pair that with something that's 2. So this still works, we just need to be like a bit smarter about it. So basically, I is less than m over 2 I plus plus. If m is even, that will cover that. Wait, hang on. So if m is if m is like 6, for example, we want to go to 3. And if m is 5, then we want to go to 2. So I guess we can do less than or equal to m over 2. Yeah, okay. So m minus I mod m. Okay, that's kind of... How does this work? So if I is equal to op, if count I is greater than 0, plus or sans. Otherwise, we don't need to do anything. Otherwise, if they're not the same, then if we don't have either, if we don't have, like, for example, if we don't have any 2s, then all we have are 4s, then we have to put all of them in individual places. Otherwise, now we have the same thing. So how would this work? Is there sort of like, I'm guessing the optimal thing to do is like say for example we have more 2s than 4s, then we would want to do something like 2 4 2 4 2 until we run out of 4s, and then we just put the rest of the 2s individually. Is there a better way to do that? I wouldn't think there is. don't see how we could do better. Yeah, it should be optimal. I'll try and I think I can prove it. I just don't really want to write it out right now. So if we have, for example, 5 2s and 2 4s, then we have to do like 2 4 2 4 2 and then 2 and then 2. So it should be this minus this. Unless they're equal, in which case then it should be 0. It should be 1. Okay. Why don't I just make a counter array? So that seems to be what I like using, even though I didn't actually use it. Okay. Let's see. So 4 6 2 2 4 4. Test case is 1 4 6 2 2 4 4. Yep. 1 7 6 2 2 2 4 2 4 2 3. Yeah. Okay. And then a couple tests for 2 6 6 3 3 3 0 0 0. Let's just give it a string. 1 5 4 0 1 2 3 4. I don't know. Guess that should be 3. Yeah. Okay. Makes sense. Bit messy, but makes sense. I can tell I'm gonna be a bit tired this morning, so it's gonna be a bit slow, I would suppose. So the face cam's working, right? Yeah, should be. Hopefully it's not lagging. I do hope it is fine. Cool. Okay, not even gonna check my place. It's probably not that good. Okay, so you're given a positive integer. You know, find k positive integers such that their sum is n, their LCM is less than or equal to n over 2. Their sum is n, their LCM is less than or equal to n over 2. So for example, we could have k equals 3 here, and here we could have more than that. And the sum of k is at most 10 to the 5th. Okay. T is 10 to the 4th, meaning that it's not going to be that easy to factor things. There will be a lot of operations. So we have like 11. What do we do for 11? Yeah, just clarification. What do we do for 11? Like, say we have... So I should expand my window again. We have 11, then we can split that into stuff like... How does this work? If we write it in binary, does that help? I don't think it would. So we can use like 5, 5, and 1. What about 13? I can pick some prime and then do stuff with it. Given constraints, the answer always exists. So we have to use at least one odd number. If we use an odd and an even, then it's not going to be that great. Can pick some anchor and then try and say that we're going to use those divisors for it. So like say we put a 5 down. What else can we do after using a 5? If we have... Let's see, if we put down a 2, not possible. 3, not possible. 4, not possible. So how's this work? If we have a 2, if we have a 4, so we can't use any number greater than 7, greater than or equal to 7. So we're constrained to the numbers 1 to 6, right? Oh, we can use 6, 6, 1. Okay, I see. Right. Okay, so for k equals 3, I guess it's sort of simpler. It's like say we have n, then we can use like n over 2 minus 1, n over 2 minus 1, and then n mod 2. Actually, how would that work? Maybe this could be odd, then that would be a problem. I guess it's fine. We could shift these so that they become even. Let's see. So c into n to k. This should solve the easy version. A equals n over 2 minus 1. So what does this give us initially? This is not going to be the right answer. I just want to see what it's doing. Okay, so 001. Okay, so LC equals n mod 2. If n mod 2 c is equal to 0, c equals 2. Alright. So actually 2 minus that would work. So then a remainder is equal to n minus c. So if a mod 2 is equal to 0, if a is odd, then we want it to be even, otherwise it has a chance of not working, I guess. So for example, say n is like 16, then we'll have 7, but we can increase it to 1. If n is 15, we get 7, 7, and 1. So if c is even, then we need to make a and b even. How do we do that? If a is greater than 1, a is odd, then that would work. Would it? No, it would not work. Because then the LCM would be weird. Alright, so alright, this is so caseworky. So if n is remainder 2 mod 4, then it works. If n is odd, this works. If n is remainder 0 mod 4, then we have a special case. Let's see. This is stupid. Otherwise, this should work, I guess. Fine. Okay, 111.224.662. Yeah. Let's just try like a lot of things. 10, 3, 3. And paste this in, I guess. This is how you construct test cases. Okay, so 111, 112, 221, 222, 331, 224, 441, 442, 551, 336. Yep. And then add another one. Zoom in. Okay, so that's good, that's good, that's good, that's good. We're good. Okay, makes sense. That'll pass the easy version. I guess the hard version is more of either an extension of this or just harder in general. I guess we'll see. Three pretests, nice. Okay, so now we need to do it for arbitrary k. So how is this going to work? N mod k is like 0 or something. Why is C2 worth less than C1? Isn't this harder? Now I don't understand. I guess we would want to make it so we use 1s and 2s or something. So if we use even numbers that are less than n and then a bunch of 1s and 2s, then it should be fine. Oh yeah, I guess that works. So we constrain it so that we should use a bunch of even numbers that are less than n. And then we use a lot of 1s and 2s or something. Is 3 like the special case? And everything else just works? So we can like assume we fill the array with even numbers. I think 3 might just be the special case or something. And the rest of it's sort of easier because things might just work out. So like for example, we can do stuff like, so we assume we initially have the array filled with 1. So let's say n equals like 20, k equals 4. So now we have 16 sum left to distribute. So we can say like, we're going to add them to these two such that they form an even number. So really we're going to add 14 and then split them, so we get 8 and 8, and now we have 2 left to distribute. And that's fine because now we can say like we're going to add 2 to each of these. And we have at least 2 of these extra numbers if k is greater than 3. So I believe this should work. Will it ever not work? If we have like 17 or something. So we have n equals 21, then what happens? For n equals 21, now we have 17 sum to distribute. This might not necessarily be able to do that. Okay, that's kind of messier. Yeah. So for n equals 3 mod 4, we have a problem. Otherwise, we should be... No, wait. How does that work? Yeah, actually, for k... So like every other case except for when we have specifically 3 to distribute and k mod 4 that we have to deal with. That's like the only hard part, right? Okay, so let's see. So if k is equal to 3, then we can do this special case. Else so if n is like 19, for example, then we have 15 to distribute. We can make it 8. We'll be happy. We will be happy, yes. If n is 18, then immediately that works. This is really the only other special case. When k equals 4 and n mod 4 is equal to 1. I think that's the only other special case. Because every other time, we can say like we have a huge list of 1s. Then we're going to raise these two to some larger even number. And everything else is just going to work out. Because now we can raise enough of these to 2s so that the rest of it is fine. But this is a problem, because we only have 2 things that we can raise to 2s. So we either have to get a 3 involved, which is not necessarily going to work, or something else. So is there an easy way we can handle this case? For k equals 4, n equals that. N mod 4 is 1. I guess we can do the same thing. So if k is equal to 4 and n mod 4 is equal to 1. And actually, this is sort of a similar special case to this. We can say that we have this, except now we have a special case, except now we have an extra 1 here. Otherwise, so let's see. We're going to pick the largest even number that works. So rec is equal to n over 2. If rec is even, if rec is even, then that means we're going to add an even number to this 1, meaning that these numbers are going to be odd, which we can't have. So if rec is even, we have to decrease it. Then a0 is equal to a1 is equal to 1 plus rec, and minus equals 2 times rec. AI is equal to 2. Okay, that's fun. So we're gonna try a lot of things now. For example, 3 3 4 3 4 4 5 3 5 4 5 5 7 3 7 4. How's this? How many is this? 7 5 7 6 4 5 6. It's another 6. Okay, this is 14. Or I could just use the line numbers, but whatever. Alright, see, oh, that's a problem. That's 0. Okay. It's negative 1. Rec is greater than 0. Right. Okay, so 1 1 1 1 1 2 1 1 1. Wait. So this is 3 3 4 3 that. Okay, 5 3 5 4 5 5. Cool. Why did it set that to 2? Why is that the one becoming 2? Oh, because it's this special case. Okay. 5, yep. So 2 2 2 2 2 1 1 1 1 2 1 1. Perfect. 3 3 1 2 2 2 1 2 2 2 2 2 1 1 1 1 1 2 1 1 1. Okay. And let's add some bigger ones. So, for example, let's see. Yep, and then 7 and then 4. Not a round number. I don't know, I'm just trying random things, hoping it works. Right. So 4 9, yep, 4 9, and then 8, cool. We get this special case handled, and that should be good. We already passed k equals 3, so it should be fine, I would hope. Keep opening this. I meant to have this on templates. Two two 1 1 2 2 2 2 1. Perfect. So yep, that's good. If it's greater than 0 and it's even, then we need to make it odd, so decrease it, because we can't increase it. And make it 1 plus rec, because if we did, then the sum would exceed n. So let me just do some stuff. Perfect. And everywhere else we have at least 3 numbers we can change. Yeah. Let's do, for example, like, what would it be? 9 and 5 or 10 and 5? Alright. Yeah, okay. Cool. Alright, I suppose we're a little slow, but we're making decent. Oh my god. Oh, that's not a good sign. So I suppose we're not supposed to use n squared memory, whatever that means. Come on. Alright, I guess we'll wait for that to load. So there are n numbers, and the n problems number with 1 to n. Ith problem is the complexity 2 to the I, a tag, and a score. After solving the problem I, it's allowed to solve problem j only if and only if the tags are not the same and the difference is greater than your IQ. Wait, what? This is like saying you're too prestigious to solve a problem otherwise. Can't click the box. What? Can't click the box. What am I supposed to do? Okay. I guess we're still waiting for that to load so I can understand this statement. After solving this problem, it's allowed to solve problem J if and only if. So the difference between the complexities is greater than your IQ, and they don't have the same tags. And then the score you gain is the absolute difference. God, this is weird. Any problem can be the first. You can solve problems in any order and as many times as you want. Oh, I see. That's why that's necessary. Do I have to refresh this again? Okay. There we go. Close that tab before anything happens. Cool. Alright, so any problem can be the first. You can solve problems in any order as many times as you want. So this is weird. What is happening here? So if you have one problem, you can't do anything. I'm scared to refresh. So the IQ then becomes the difference in complexity. Cool, okay. All right. Guess the reason they don't want you to have large memory is because you can make it like longest path or something. So when we go from one problem to another, this is very, very contrived. This is weird. Should check the dashboard actually. Maybe E1 is easier. Might as well use the dashboard since I'm sure we're very behind right now. So say all the tags are different, then what will be the best strategy? Awesome. So what would be the best strategy? Are these the... You have another dividing the array. Okay, let's read both, see which one's easier. In this version, k equals 0. So you can change the values. There's an array of positive integers. You should divide it into a minimal number of contiguous segments such that in each segment there are no two numbers whose product is a perfect square. There are no two numbers whose product is a perfect square. Are we supposed to factorize or are we not supposed to? 10 to the 7th is basically taunting us to do that. So I guess we should. And we do the standard like bitmask stuff. Okay, this doesn't seem that hard. Seems like some classic segment tree stuff. So the idea is if we represent a number in like terms of its prime factors, so for example, 18 is equal to 2 times 3 squared, then because this is a square, if we multiply it, it's gonna like, we're interested in if the numbers are perfect squares. So we can sort of just ignore everything that's a square. And say we have like, for example, something like 2 to the 5th times 3 to the 7th times 11 to the 9th, or 11 to the 8th, right? It's not a possible number, but the point is we can ignore everything that sort of like contributes to the squares. So then basically we can make this just 2, because 2 to the 5th is equal to 2 squared times 2 squared times 2. And because these are both perfect squares, we can ignore them. So we can make this 2, we can make this 3, and then we can make this nothing. Pretty sure that's the wrong symbol, but whatever. I choose how to draw things. So basically we reduce it to like either it has each factor or not. And then for the product to be a perfect square, they have to have exactly the same set of factors when you take all the powers modulo 2. Yeah. So I'm guessing more people are gonna solve this because this doesn't seem that bad. And now basically now we have a segment tree problem. Right? Yeah, so basically for this, we let dpi equals answer for I. Also here, if we have a change, then we can basically like remove it, right? Because we can change it to some massive prime that we haven't used before, and then now we're like golden. So n log n k squared is not going to be nice, so we have to do a bit better than that for the hard version. But for the easier version, it's going to be the answer for the prefix 1 to I. Then say we're here. Then this might match with some number to the left of it, or it might not. Then the number to the left of it might also match with some number to the left of it, or it might not. And then say we do have this number here. Then we can't have both of these in the same interval. So the interval we're constrained to is basically everything over here. So I guess we can do this with descent, or we can just do binary search. Can build a sparse table, which is something I've never done before. Yeah, we're binary searching on this interval. So if we have each index be like a value of the previous occurrence, or a -1 if nothing, then we're binary searching on the longest suffix of this prefix of 1 to I, where all of the values are less than or equal to the length of the suffix, or all of the values are like outside. That's the idea. So we don't have any duplicates. I guess we can build a sparse table and do that in n log n. I have a sort of strategy for this, but it's gonna be easier to do this problem. So, can I submit? Is this page gonna load? Okay. Alright, well we can solve this and then let it be for now. So reading to n to k for... This is gonna help with E2 later, so we can just have that for now. And number theory. Just copy it in. What I'm going to do is get this factors thing. So facts. Please wait. Okay. Let's see. 2e5. Also never built a sparse table before, so that's gonna be cool. Wait. Right. Okay. So we do a map of a vector. No, wait. Yeah. Map from a vector to an integer of last. Okay. So facts I is equal to, alright, equals, alright, also I need to call gem primes. We need to do the sieve, then we call this factors thing. I have this just to make sure I actually do things. So factors AI. So map count for LXF plus count X. If x dot second mod 2 is equal to 1, so if we have an odd prime power, then facts I dot push back x dot f. So now we have this. These are guaranteed to be a sorted order because that's how maps work. So now, if last facts I is not equal to, all right, if last has facts I, then let's see. So I can say like bi is equal to last facts I plus 1. Else bi is equal to 0. So we're having bi be the longest prefix that works, basically. And then we want we want maximum query. Okay. Then last facts I is equal to I. Now we build a sparse table, which is again something I've never done before, so it should be fun. I0 is equal to AI. No, BI, right? Yeah. Then what we want is we want it so there's no number that's like larger than the values that aren't contained in the suffix. This is going to make sense later. I'll explain it. But right now what I want is the page to load. Okay. The standings work? I'm assuming why would the standings work? That doesn't make sense. That's a text. Okay. Now for LL j is equal to 1, j is less than max, j plus plus. For I equals 0, I less than n, I plus plus. So if I plus, if we're out of bounds, then don't do anything. That's the idea, right? So if I plus 2 to the j is out of bounds, don't do anything. No, wait, this should be minus 1. Because that's the right boundary. And there's that, is out of bounds, break. Hair's getting messed up. Otherwise, so stij is equal to max stij. No, it should be I j minus 1, and then sti plus 2 to the j minus 1, j minus 1. Okay, then while 2 times r yeah. SP2, do the M sites work? Guess we can. I want to see the dashboard though. Alright, whatever. So the smallest power of 2. Okay, send it for each tab. Jesus. Have that be equal. I is equal to R. Because we need the smallest power of 2, right, to use for the sparse table. Wait. 2 times. We need that. Okay, actually, let's just make sure this works. No multi-tests anymore. Not for this problem, at least. What? Oh, because I didn't actually. Are we fine? Okay. 0. What? No. Alright, so 1. That does not make sense. Wait, 2. Oh, right, yep. This should be 0 as well. That makes sense. Okay, so 0, yep. Then 1, 1, 2, 2, 2, 2, 3, 4, etc. So this, for example, represents the range 4 to 7, which is correct. Cool. Okay, now we do some DP stuff. So now we actually do need a segment tree, because now we need to do some RMQ, some range minimum query, meaning that we need that. We're going to have some contiguous range that works. So seg tree min t. Let's see. Actually, wait. How's this gonna work? Okay, that's weird. That's trippy. st.init and c. How's this gonna work? So sp2 r minus l plus 1. Let's return min st lx str minus 2 to the x plus 1 x. Right, say we have the range 1 to 5, so the largest power of 2 is 4, so we need this to be 2, so we can do that. Okay. Yeah. The best, so LV is 0, RV is R plus 1, while LV is less than RV. If RMQ MV RV R is, and that should be max. We need max for sparse tree, minimum for, yeah. So if the largest value is greater than MV, then we need to shrink the interval. So LV equals MV plus 1, else RV is equal to MV. Return, oh wait. Yeah, okay. Should be good. I'll test it all later. So how am I gonna do this? So I guess we can make this 0. Confusing myself. Okay, so we're gonna have some indices in the segment tree. So we have this range that works. Then this needs to represent dp of this. So this, the value of this in the segment tree is dp of I minus 1. This is dp, for example, of 0. So that if we have this, then we need to query the rest of it. This is like a special case. And then this value needs to have 0. dp 0 is equal to 1. C0 is equal to 1. No, that needs to not be 1. So st.update I dp I minus 1. Right. So now so dpi is equal to that. Better if it wasn't so trippy, but I guess it must be. So this has to be dp0. So when we're here, we consider taking only this position where we use the last one. Oh wait, we do have multi-tests. Everything has multi-tests. Does site work yet? It does, okay. So I guess we can check the dashboard now. I'll check that after I submit this first. So we do need multi-tests, which is annoying. And just gonna put this here so we don't do it for every test. So let's see. This is being reset. This is being reset. Sparse table is being reset. Kind of. Yeah, it's like 20 times n each time. This doesn't matter. This we do need to clear. Last, clear. This is fine. This is fine. Okay. Did I call it best? I don't even remember. I did call it best. Okay. Why do I have C? What? Oh wait. MT. 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 Right, because this is an array, so we can't really do that. Cool. All right. Let's figure stuff out. So let's just debug everything first of all. Make sure everything is working as planned. So let's see. For I equals 0, I is less than n, I plus plus. So we want to print the factors. Facts I, bi. Cool. And that's not gonna work because I didn't close out that loop. So I can put these here. Okay, so we get 2, 2, 3, 2, 1, nothing, nothing. Okay. So this, for example, has nothing, this has nothing, this matches with this, so this has to be a 1. Yes, so this works here. Oh wait, hang on. Now I'm very confused. I think this is the problem. I should just have it be that, the previous index. Then -1. And this would say, yeah, I don't know what I'm thinking. I think that should work. Indeed it does. Okay, so 2, -1, 2, 3, -1, 2. The previous is 0. Here, -1, here we have 3. So this we have to split up. We have to split it up like that. Okay. Now here, this is just a single element, so that's fine. And this works for everything except for like itself. So these have to be separated. Okay. Come on. For j equals I, j is less than n, j plus plus. Just to test the sparse table a bit more. Just to make sure everything works. So let's see. 0, 0, -1. So 0, 0, and 3. Yeah. Everything there should have 2. This is all -1. And finally, the last check. 2, 2, 3, 1, 1, 2, 0, 1. Perfect. So let's see. I'm going to take the factors, make the counts. If it's an odd count, put it in. It should be sorted automatically. Now, if we have this, then set this to the previous occurrence, otherwise don't. Then now set the previous occurrence to this. Make the sparse table. Yes. Cool. CI equals 0. Make that there. At some point I should template sparse table. I've just never written this before, so it's sort of not something I can do immediately. So set CI equals 0. Set this to the previous DP value. Because the segment tree represents like the possibility of having the ending point be here, meaning that everything else has to be accounted for if this is the ending point. So yeah, then we take the best, and then the DP value is the RMQ, or the range minimum query. R minus 2 to the x, and then plus 1 because we have to do indexing. Yep. $200,005. Everything should be good. Okay, epic. As expected. So it does take a long time, potentially because of the factoring. So what? What have I done? It should be binary searchable, right? If we extend the interval, the max can only increase. The range can only decrease. If we reduce the interval, the max can only decrease. The range can only increase. Should be monotone. Make sure best eye works. So 00114, 0003. Wait, what? That actually doesn't make sense. Fax I doesn't make sense? I don't think it does. Wait, hang on. Why does 1 have the factor of... Have I messed up factorization? Is that really what's going wrong here? Wait, what is happening? How did I not notice this? AI. What? Okay, that part's right. Somehow this is being messed up. 2, 3. What is happening? The map must be messed up somehow. Oh my god. Multi-tests, damn it. I forgot about that part. Okay. No. Alright, that was dumb. That should not have happened. That was really dumb. Yeah, now it makes sense. Alright. Whatever. What can you do? What you can do is cry. Yeah. Okay. Alright, we can try and solve D now. Wow, a lot of people solved this. Jeez. Guess it do be that easy. Alright. What can we do now? What can my tired old brain pump out at this stage? Right, so if we're at a problem, also wait, how would this work? Would this be easier? I guess the longest part is the factorization. So we can basically remove some elements. If we have some partition, can we use it to make our partition better? Every element in the partition should contain like exactly. So I just realized we can probably do greedy here. Yeah, it is sort of greedy because DP should be monotonic, I guess. Okay. Yeah, okay, I just realized you don't really need a segment tree. I guess you can just do greedy. I think that's how it would work. So, now what? Well, we can say that, like, We have the dp value. Can't have like a dynamic sparse table, right? If we like insert elements in the end, I don't think. No, that's not possible. Is it? I'm not sure if it is. I think it affects too many things. And the point is to avoid n log cubed. That's the idea. Or nk squared log n. Because that's not going to be good. I think there were a lot of easier ways to do what I did for E1. Okay, well, not sure. We can try D though. So there does exist some sort of like n cubed dp, but that's not great. I guess 5,000 squared is designed to be too big. Yeah, so they want us to use like linear memory as some sort of thing. So the last problem we solved was like something. The last problem we solved was something. The only other thing that really matters is the problem you solved before that. Because we know that's going to be the largest value of the IQ every time. Ow. Oh, jeez. So the largest thing we ever use is definitely important. Can't tell if the square function is arbitrary or if it matters. think it should matter. Alright, so it's, say you're at the one with the larger complexity, or rather the later one, the larger index. You can go to any problem that's like number of moves you make is OFN, that's also a thing. What kind of a thing is it though? So if we go forward, so what's the strategy for the second test? For example, so 1 to 2, 2 to 3, 3 to 4, 4 to 1. I see. Right, but the scores can be arbitrarily ordered. I'm actually just supposed to do some memory optimization or something. Don't understand. For some fixed, like, right point. Round is extended. Okay. Cool. At least I didn't have problems submitting because I was busy overcomplicating everything. So that is a bonus. So for example, here we can do something like 2 to 19, 19 to 1. No, that's dumb. Like 8 to 19, 19 to 2, 2 to 1. No, this should be a better way. Like 2 to 19, 19 to 1, 1 to 8. Alright, so 7 plus 18 plus 17. Wait, what? Yeah, 7 plus 18 plus 17. Okay, that's right. So that's how we get 42. So we do have all sorts of restrictions here. If we can go from a place to another place. What matters here? That's sort of the key. What matters? We base it off the largest thing we had. Then either we are already there, or we made some jump from there to somewhere else. Like for example, so we like make this jump here. So what if we like can iterate over the largest thing? Then we say we came from some previous thing. So now sort of if we know the best value for a sequence ending at this thing, we know that automatically it's going to like be within this interval, I guess, because we haven't introduced this until now. So then it's the possibility. What does that mean? What does that help? So if this sequence is going to be better than it was before, then it has to use this one. And it can only use that one if we didn't come from a place with higher complexity. Interesting. I guess that does give us an idea. Okay. This is the tag, and this is the score. All right, now. First of all, we can say dpi equals 0. So this is the new largest point. So for each previous point, R max is equal to 0. Ji minus 1, j is greater than or equal to 0, j minus minus. So first we consider jumping from here to j. So if ai is not equal to aj, then dp of j is equal to max dp of j, r max, actually this can just be dpi plus abs ai minus aj, then dpi equals max dpi dp j plus abs ai minus aj. Wait, hang on. Should make sure we don't actually do that. Yeah. Might. I think that works. Because we can like go from here to here, or we can go from here to here. We can go from here to here, only considering that the previous jump we made was from one of these locations. So we take that maximum, and then, so we consider that jump. But we can also jump from here to here, assuming that we somehow ended over there. Yeah. Because we can always jump from here to here, because this is the new largest value. That's because the complexity is 2 to the I. I don't need that. That's weird. What am I printing? 1666746. Oh wait, this should be the values, not the tags. Cool. And this is linear memory, n squared time. Yeah, I mean, I don't see what's wrong. Proof by can't find a counterexample. Okay, let's just make sure, right? So we can jump from here to there only if the previous jump we made was smaller, meaning that first we consider only the transitions here and we keep a running maximum of those. And we can also jump from there to here at any point, because it doesn't matter where we came from here, because we know the previous jump we made was somewhere within this interval, which has a smaller cost. So this cost, the cost, like the IQ required for this red jump, is always going to be higher. So it's going to be always possible. So we can always consider that, as long as the tags are not the same. As long as we can actually do the jump, then we can do the jump. That makes sense. Cool. Alright, now we can try to solve E2. I can refresh just to make it less scary. Alright, so the only difference is that in this version, K is at most 20. So we can go to my submissions and copy in E1, perhaps. Because even if it's overcomplicated with segment tree stuff, it still has the utility stuff I used for it, like the number theory stuff. So let's see. You can change it, so you can basically remove values from the array. If you can remove values from the array, what does it mean for you? Remove values from the array. Oh, they made the round unrated. Alright, that's unfortunate. So this screencast is gonna die, but fine. Okay, well, I'm assuming the ranking still isn't gonna be nullified because I'm basically competing against the Div 1 people and they wouldn't have given up anyway. So let's just see what we can do. I think we can speed up to nk log n, maybe. We can do descent. We can do segment tree descent and make it nk log n. Like, it's very ugly. K equals 20 is concerning because it means it sort of suggests that that's what they want us to do. I don't like that. Although maybe we don't need the sparse table. I think maybe there's something better we can do here. I think we can maybe like keep track of the intervals or something. Okay, so what can we do? Keep track of the intervals. Yeah, you can keep track of the duplicates. But that is also very ugly, right? Well, if we have a duplicate, it will never stop being a duplicate, right? That is also true. I guess it's not that bad, because it's mostly just iterating through a set. Okay, sure. All right, so this sparse table is very stupid. Let's just get rid of all that. Yeah, we don't need any of this. This is very not necessary. So I'm going to like totally get rid of this in the explanation. So don't worry about it. We still do need the segment tree. This can be expanded. We know DP is monotonic, so I don't even think we need the segment tree actually. Right? Because DP has to be monotonic. That is like the later ones are greater than the earlier ones. Okay. Set hello dupe. So dupe dot insert that. Also dupe dot insert -1. Dupe dot clear. I don't think we need the segment tree. Yeah, we should not need the segment tree. Because the earliest index we can find is always going to be the minimum one. So auto it equals dupe.end. For j equals 0, j is less than or equal to k, j plus plus. Alright, so for j equals 0, j is less than or equal to k, j plus plus. If I is greater than 0, no wait, I can say something like if I is greater than 0, So it should technically be n times k plus log n. Sure. V equals dp I minus 1j. dp ij is equal to v plus 1, just as an initialization. Okay, so, right, then we do this necessarily. 0, j is less than k, j plus plus, dp ij right. Otherwise the transitions don't make as much sense. Actually, wait, how does this work? So we have k, maybe it's k squared, that's fine. As long as we don't overdo it. Yeah, that should work. Okay, so if it is equal to dupe begin, then we can't go any further, so break. Otherwise, minus it. Pause is equal to location of the iterator plus 1. So now the pause is the previous dp value we're going to rely on. It's the start of the interval we can have. So for ll, l equals 0, l is less than or equal to k, l plus plus, or rather j. So dpil is equal to min dpil dp pause l minus j. Actually, that should be fine. Yeah, we should not do that. Okay. Don't need that anymore. So this is 1 1 1 1 2 1. Okay, so what's with that? Don't need this. Yeah, okay. So let's see, 2 3 2 2 2. Okay, so if we use no operations, it should be 1. If we're here, this is a 2, so we can have that be fine. This should be a 2, this should be a 3. So that can be fine. That can be fine. This does nothing. This does become a problem. Now if we do that, that's fine. So we need 1 2 3. What am I messing up here? So if we use 2 operations, okay. For here, how does this work? Can use anywhere from 0 to k operations, right? So let's see. So for example here, 2, 2, then 2, 0. Right, yep. So 3, 3, 3, 2, 3, 0. This is 5, 5, 5, 3, 5, 2, 5, 0. So what's with that? 7, 5, 7, 3, 7, 2, 7, 1, 7, 0. Why is that still 1? Should not be a 1. Oh my god, wait. Wait, how? Wow. Wow. How did that possibly work? Okay, that's worse, but something's changing at least. Okay, so what? So doing a single operation is automatically like a cost now. Oh wait. Okay. This should all be 0. Alright, so 4, 3, 1, 1, 1. Yeah, now we get 4. Now we have 5. 1, 2, 3. Wait, why is that 4? 1, 2, 3. Now that's wrong. Okay, nice. Something is up with that. Alright, hello. Yeah, we need the same thing here. Good thing we checked that. Wait, okay. This has to be that. You can potentially extend the previous ones here, right? Yes. So this is sort of initialization. Pause. -1. But now we're actually using the right one. So I think this should be the correct value. We said like this has to be the correct value. So we consider just using that as a possibility. No, this should be 0 too. What am I thinking? What am I thinking? Yeah. Alright, now does this make more sense? So this should be 3, correct. This should be 4. This should be 4. This should be 4. Yes. That should be 5. So now I have to split that. That can be 5. That can be 5. Now it all makes sense, I hope. I guess we'll find out, but... So we'll get the right answer on the samples now. So 1, 10, 3. So answer should be 7, yeah. Alright, so now what we can do here is, let's see, what can we do? Well, we can remove these, wait. So this can form a segment, that can form a segment. This can, this can, this can. So I'm guessing the best answer we can get is 4. Yeah. Okay, let's just look over everything again. C into AI, facts I.clear. Make it the factors, make it the count. Do the same thing we did last time, that's fine. Last facts I equals I. Yep, so now we consider the case where we just don't extend it at all. And in fact, I don't think this is necessary, but I mean, we might as well. And then now we consider some other cases where we potentially, yeah. Alright, sounds good. A lot of DP here, it seems. I did DP on E1 even though I wasn't supposed to. Or even though it was easier than that. Guess that's how that goes. Cool, finished in the span of 2 hours. So we would have been done with the contest anyway. Alright, where do we end up? Cool. Okay. Not that bad. Surprising for how dumb I was on E1. Rather slow throughout, but that's fine. I mean, still did pretty good. Would have been faster, but can't complain that much. Yeah, other people had a worse time. What? Oh, he must have solved C at last. Interesting. He went for E2, E1, then E2 a lot later, and then just stuff happening. Cool. How are my other friends doing? Seems rough. So like basically everyone solved E1. It's the next step. Yeah, pretty good. Pretty good. Despite being slow on everything, still pretty good. And it seems like, I guess other people overcomplicated E1 too. Like he took, oh, he did E2 before anything else. Seems like we're one of the slowest guys to AK. But not the slowest. And I can take pride in that. There are a couple other people who have even worse penalties. They do it backwards. I know people do that sometimes. Did E incredibly quickly and then just spent a long time on D, I guess. How's the room? Cool. All right. Well, that's a wrap. So I guess we can do solutions now. And again, even though the round is unrated, I still think it's at least a good idea to try and upsolve, because these were problems that could appear on the div too. Like, there was no issue with the round itself. It was the technical problems that caused it. So that's unfortunate. I feel bad for the authors now. These were cool. I liked D. I don't know about E2. I'm not sure. I haven't seen it before. That's my usual complaint, so I don't have that complaint, but there might be other complaints to make as well. Okay. Cool. Let's do some stuff. So you have an array. You have an array, for example, 4, 20, and then 13, 37, except these are all single digits. I'm assuming they also have a 69 in there somewhere. Yeah, okay. Right. And what we want to do is reorder it so that the sum of the mexes of the prefixes are maximized. So the mex is simply the smallest element that's not in the prefix. So for example, here the mex would be 1 because we have a 0, but we don't have a 1. And on here, the mex would be 3, and on here, the mex would be 5. And then we can never get a mex of 6 because we don't have a 5. So basically the idea is, say we want the mex to be greater than 0. Then somewhere in our prefix, somewhere in this prefix we're working with, we have to have 0. Now, if we have a 0, then we want to make it so we make as many mexes greater than 0 as possible. So what we want to do is put it at the beginning. So now, if we have a 0, we can move it to the beginning. Otherwise, if we don't, then it doesn't matter what we do, because no matter what, we're not going to have any 0 anywhere. So the mex is just going to be constrained to be 0 no matter what. So either we have a 0, then we move it towards the beginning, or we don't, and we're done. So let's assume we're working with that. So now we have the same situation here. We want the mex to be greater than 1. So either we put a 1 on this, either we put a 1 at the beginning here by the same argument, or we don't have a 1, so we can't do anything. So I'll put the 1 down. Then we want to put a 2 here or do nothing. Put a 2 down, put a 3, put a 4. Then now we don't have a 5. So because none of these elements can further affect the mex, because we don't have a 5, we can put them in any order we want. So for example, I just put them like that. So the way I did this was just to simply keep a count array, count of ax is equal to I. And then you can basically see if you have at least one 0, put it down. If you have at least one 1, and then once you don't have anything else, then put down any element that exists. So you just need to search for any element. And this is fine because it's O of n's n times 100 times t, but it doesn't really matter because it's values are small. Yeah, so basically that's it. Make this sequence of 0 to something, and then for the rest of it, put the elements down however you want. Cool. All right, now we have B. This one I misread, which is why it took me a while. Okay, so basically you have an array of some numbers, like 2, 2, 8, 6, 9, 4. And you also have some parameter m, for example, m equals 4. And you want to rearrange, and you want to make some new arrays from this array, so that the way it works is the difference between adjacent elements is always divisible by m. So first things first, divisibility. If A divides B, that's the notation. So A divides B, then that's equivalent to B mod A is equal to 0. So since we only care about mods, first we can take all these numbers mod m. So take all the numbers mod m. Then we get 2, 2, 0, 2, 1, 0. Okay, so now we want the sum of these, and because the numbers are mod m, they're always less than m. So now we basically want the sum of these to be either 0 or m. So we can only have the sum be 0 if we have the zeros. Right? So we can, like, for example, we can put all the zeros into a single array, and then all the adjacent differences will be 0. And then that's perfect. And nothing else can match with 0 because anything non-zero adjacent to anything that's 0 will give you a sum that's not 0 or m. So it doesn't work. So we put all the zeros into their own array. We can sort of treat it like a special case, although it's just depends on how you do it. Then everything else sort of needs a pair. So there's also one more special case. If m is even, then m over 2 can also only pair with itself. For example, 2 can only pair with 2's. 2's can only pair with 2's because that's the only thing that makes the sum be m. So really, if m is even, we can also put m over 2 all in the same array. And let me stick in a few more elements. So for example, say we have a 7 here, then we can say we have a 3. So now, if we put this 1 in an array, it can only be paired with the 3. Anything else will give it a different sum. So any other value x, where x is not equal to 0 and x is not equal to m over 2, if m is even, can only be paired with m minus x. Because then the sum will be m. The sum of these is m, and you can't have 0 because x is greater than 0, or x is not equal to 0. So this is the only pairing you can make. So really, like, every group of x and m minus x is now independent, because none of these other pairs can, like, mess with each other. Like, the 2's can't mess with the 0's, the 2's can't mess with the 1's, the 0's can't mess with the 1's, but the 1's can mess with the 3's. So really, now we need to solve the problem for just this. For each x and its corresponding m minus x, we need to solve the problem for it. We also need to make sure we don't overcount. So we need to not count both x m minus x and m minus x comma x. So we just make sure that we can just force this to be less than or equal to m minus x. And that way, less than or equal to or less than, depending on how you treat the ones where they're equal. And so basically now, that basically just assures us that we're only solving for this. Because now this is not equal to this, based on how we handle special cases. Okay, anyway. So let's say, for example, now we have a certain number of 1's and a certain number of 3's, and we need to move them into arrays. So how do we do that? Well, for example, let's assume without loss of generality that we have more 1's than 3's. And now let, for example, C1 is equal to like 3 and C2 is equal to, for example, 1. Then one thing we can do is we can say we can have 3, 1, 3, or no, sorry, wrong thing. Also, this is very wrong in every way, shape, and form. This should be the count of 3's. And it's sort of confusing because these are the numbers I'm using. But basically, we can put the 1 here. We have to put this 1 somewhere, right? So now, if we're going to put a 3 with this 1, we have to put the 3, for example, here. So now we can stick another 1 on because we have this 3 here. So now we have 1, 0, 1, 1 remaining and no 3's remaining. So the other array we can make is this one. So let's see. Say we get a bit more complex. Say we have 7 1's and, for example, 2 3's. Then I claim that the best way to do it is still something like this. 1, 3, 1, 3, 1, until you run out of 3's, and then make the rest of them 1. The reason is as follows. It's like, say you had some other partition. Then either it would end in a 3, or it would end in a 3. Like, for example, either it would end in a 3, or it would end in a 3, 1. Say it ended in a 3, 1, right? Then we can stick it onto this and get the same answer, because we already have both of these arrays. and say it ended in a 3, then that means that like we have this 1 here that's sort of alone, and we can put it onto the end of this array and then reduce our answer. So we can assume that the optimal answer will first of all not have anything ending in the lesser count, and then also not have anything ending in a group that we can sort of stick on to the first array, because we get the same answer if we do that anyway. So really this is the best way to do it. We create this pattern until we can't anymore, and for example, if we have an equal number of 1s and 3s, then the answer is still just 1. That may be a special case, so beware. And otherwise we can create this pattern and put down the majority element otherwise. And if we have more 3s than 1s, then we would do something like this and then do the same thing. So how many arrays does this create? Well, so we use one array, and this array has how many 1s does it have specifically? Because we're interested in the 1s, because this is going to be formed with the remainder of 1s. It's going to be this has the count of 3s or the count of the opposites plus 1 1s, and then each of these has 1. So the number of arrays we use is C1 minus C3. Yeah, that's basically the idea. Because the number of 1s we have remaining is 1. The number of 1s we have remaining after we create this array is C1 minus C3 plus 1, which is equal to C1 minus C3 minus 1. And then because we have an extra array here, we have to add 1 on, and then we get C1 minus C3. That's how that works. So really, like for each pairing, we can just add like, it's like the maximum of 1 and C1 minus C3, or this should be the larger one and this should be the smaller one. Yeah, that's the idea. So in code, it's sort of like basically handle the special cases where you like we find the opposite and we take it mod m. So if it's equal, then it's either 0 or it's m over 2, depending on how that works. Then we only need one array for it if we have that element at all. If we don't have that element, don't do anything. So otherwise, we consider each pair. If for example, we don't have any 3s at all, then actually the formula still works. So it doesn't really matter. But yeah, so actually we don't even need that special case. But otherwise, we let A be the maximum and B be the minimum. Then either we have, it's basically adding the maximum of 1 and the count of the larger minus the count of the smaller. So that would be the idea. I just broke it into if statements because it feels like it's easier to follow that chain. But I mean, you can do it however you want. Also, I think, is n small here? No, it's big, but that's fine. Okay, now we get to the fun part. So this one I just like bashed together a solution and made it work. And I'm not even sure if it's intended. I don't know how like nice it is, but it is something. So that is an idea. So basically, like, this statement is as simple as it can be. You need to create an array with k integers such that their sum is n and their LCM is at most n over 2. The least common multiple. All right, so the first subtask, C1, is specifically only k equals 3. So one way to do this is to simply say, let's look at the let's look at the samples, right? Okay. And actually, we can work out some small cases too. For example, how we do 13. I think this is like the only way we can do this. The only way we can do 13, or like one of the only ways, is to make it so we have 6, 6, and 1. If we were doing 11, we would have something like 5, 5, and 1. If we're doing 9, we can do it such as 4, 4, and 1. Or we can do 3, 3, and 3. But for some of the more complicated numbers, like for example large primes, we have to have it be not like divisors. So this can be, for example, 8, 8, and 1. Do you see where I'm going here? So this is the idea. So for example, for odd n, then we can have the floor of n over 2, the floor of n over 2, and 1. And I don't have a good way to motivate the solution. Like literally all I did to figure this out, what I did to figure this out was I looked at 13, I saw that this was the only possible solution, and I'm like, hey, maybe that could work. And it turns out it does, because the LCM of anything in 1 is itself. So if both of these numbers are less than or equal to n over 2, then we can stick on this 1 here and it'll be fine. So for odd n, this always works. What if we wanted to do even n? So for example, say we had 14. 14 is, okay, we can do 6, 6, and 2. So we had 18, we could do 8, 8, and 2. Say we had 10, we could do 4, 4, and 2. So it almost like works pretty nicely, right? But if n is a multiple of 4, then we sort of run into problems, I think. Wait, do we? Yeah, we do, I think. Because we could, for example, have 4. Also, these numbers have to be even. If these numbers are odd now, then it's not going to work, because like LCM of even and odd is going to be large. So these numbers have to be even. So for 12, and specifically for any number where n mod 4 is equal to 0, then we run into this problem where these numbers are forced to be odd if we want to have a 2. So for example, to make this work, we need to have 5, 5, 2, but that doesn't work. So instead we can have 4 and 4, and then what do we put here? Well, this can be a 4. But then if I take some different number, then this would be a 6, and this would be a 6, and it doesn't work. Because the LCM of this is greater than 16. It's 12. So it's not guaranteed to work for certain numbers. Luckily, for n mod 4 equals 0, we can do something even simpler. We can do n over 4, n over 4, and n over 2, sort of inspired by the construction in the sample here. So for this, instead of doing that, we can do this thing that's guaranteed to work, something like this. And then for 16, we can do 4, 4, and 8. So basically that's the idea. So odd n, we do this no matter what, it always works. If n mod 4 is equal to 2, then we can do something like n minus 2 over 2, n minus 2 over 2, and 2. And this will always work because this is always going to be even in the way we construct it, so we can stick a 2 on here. And then otherwise, if n mod 4 is equal to 0, then we can simply do n over 4, n over 4, n over 2. So it's a bit messy, but it works. Now C2 has an extra constraint. Which color did I use? That k is between 3 and n. Right, so for k equals 3, we solved it. What if we did a similar idea though? What if we had two large numbers, and then the rest of them, we made them something that wouldn't interfere with the LCM, right? So something that would be nice is if we can always make these numbers even, then say we have these two large numbers, then for everything else, because they're even, these can be either 1 or 2 for each one, because 1 doesn't interfere with the LCM at all, and because these numbers are already even, 2 is not going to touch the LCM either. So the LCM is still always going to be less than or equal to n over 2, provided that these two numbers are less than or equal to n over 2, which they are because they're even. So that works out pretty nicely. So really, a thing we can do is we can, because k is less than or equal to n, we can always start with this array being all 1s. And then we sort of need to distribute m minus k values among the rest of them. So we can raise these to the largest pair of even numbers we would want. There's a bit of math involved in finding this, but it's not that bad. I think it's something like you can do floor of n minus k over 2. And then if it's, this is the number we're going to increase by. So if it's even, then decrease by 1. Because we need this increase to be odd so that these numbers can be even. So that's our number, call it x. Then now we have these two numbers being x instead of 1. So now the sum we have is n minus k minus 2x. And we need to distribute that among these numbers. But the idea is that this is always less than 4, because say it was greater than or equal to 4, then we could increase x by 2 and then decrease it by 4, and we would still satisfy, it would still like be a valid array. So we can assume this is less than 4. Right? So now we can just raise some of these to 2 to make it work. So for example, say like this value was 3, then we can just raise 3 of these to 2's, and again, it would not change the LCM. So that's perfect. The only case where this is a problem is when this is equal to 3 and k is equal to 4. As it turns out, the way the math works, this only happens when n mod 4 is equal to 1. But in that case, remember we had this other special case before where n mod 4 equals 0. We can do the same thing here. We can say that we have 1 and then floor of n over 4 and then floor of n over 4 and then floor of n over 2. And it's basically like saying we have this case except we stick on an extra 1 at the end. Because if n mod 4 equals 1, then n minus 1 mod 4 is equal to 0. So this sum needs to be n minus 1, and we have 3 elements. So it's basically saying we're solving for n minus 1 with k equals 3. So as it turns out, this is the only special case. For everything else, we can do this strategy. We can make these two numbers x, and then everything else we can add either 1 or 2 to them to make things work. Or we can like make them either 1 or 2. So implementation wise, first we handle k equals 3 special in a special way. So if n mod 4 equals 0, do this. Otherwise, just do some math. It's basically like, because C++ uses floor division by default, it's like pretty nice. And otherwise, so we have this special case, and otherwise we find x, then we set these values to that, then we find this new value, and this is equal to n minus k minus 2x. And then we simply, while we need to, set as many values to 2 as necessary, and then print them. Okay, so this is where it sort of gets more interesting. I don't know, actually C was kind of cool. A lot of special cases, I'm not sure if that was like the intended solution. Maybe it was nicer, but I don't know. Right, so now we have this, and basically the idea is we have this array that we are working with. And this array has like 3 different things, but the input is only 2 because one of them is given to us. 20. Move this a bit down. How does it get stuck on that? Okay. And also each thing has an implicit like complexity to it. That's what they say. Where the complexity of I is 2 to the I. So for example, this is 2 to the 0, this is 2 to the 1, this is 2 to the 2, this is 2 to the 3. 0 index or 1 index, it doesn't matter, because this is just like a constant multiple of everything. Right, so what we're going to do is we're going to start somewhere. Then we can jump from here to another place. Only if, first, these red values, let's call them T, let's call this, we'll call this C, actually wait, call this C, call this T, and call this S. I think that's what they use, right? Yeah, tag, sure. So we're going to start somewhere, and we can jump from a place to another place only if A, the tags or TI is not the same. So we can't make this jump because these two are the same. Second, the absolute difference between the values of C is greater than the absolute difference for the last jump. So for example, say we did this jump beforehand. So this gives us a difference of 7. And then now we do this jump. Then this gives us a difference of 3. But that's something we can't do, because 3 is less than 7. It has to be strictly greater, meaning that we also can't make the same jump over and over again. And yeah, and then when we make a jump, the benefit we get for it is the absolute difference between the values of S, not the sum, the absolute difference. So we gain plus 5 minus 15 is equal to plus 10, or the absolute difference of that. Right, so we want to figure out, of all paths, what's the maximum score we can get from some path, or the sum of scores, like the sum of benefits we get from each jump. All right, so this being 2 to the I is important, because one thing to note is that, say we make a jump, how do I explain this? It means like the jumps we're gonna have are sort of like a special, sort of have like a special structure. If they were not 2 to the I, then we would have problems. I think it would require like an n cubed dp or something, but that is not the case here. And also, by the way, the memory limit is 32 megabytes, so we only get O of n memory, basically. I'm not tired at all. Okay. So how do I say this? Basically, there are two like different types of jumps. There are jumps that go backwards from a value to a smaller value, and there are jumps that go forwards from a value to a larger value. Now, say we do a backwards jump. What it means is that now we can only do a forwards jump from here, because if we were to do another backwards jump, because of the way binary works, this distance is going to be at least 2 to the, it's going to be at least like this over 2. So it's going to be at least 2 to the 2 over 2. And then everything over here is less than or equal to 2 to the 2, less than or equal to 2 to the 2 over 2, because of the way powers of 2 work. That is a less than or equal sign. So now what we were like sort of forced to do is we can so the absolute difference between any of these two elements is going to be less, or is going to be less than or equal to this. Meaning that we can't make that jump because we already made this jump of size this over 2 at least. So when we do a backwards jump, we can only ever do a forwards jump. And we can only do a forward jump to a larger index than the previous one we ever encountered. Right. So with that in mind, now we want to construct a sort of DP solution. And the fact that n is like 5,000 means it's either like brute force or some sort of DP or something. So that's the idea. What we can do is basically we can say that, assuming they're leaving, for example, let like dp of I and j be the best score where the previous jump was from j to I. Then the transition is simply jumping from I to some new number such that it works. Right, so this has n squared states, so it's n squared memory, and it has n cubed time. But we can do better. And the reason is because these costs are powers of 2. So let's say, for example, this was the largest value we ever had, meaning we didn't visit anything to the right of here. Then the way this works is basically saying like when we're right, so this was the largest value we ever had. Now, say we're now going to introduce this value, meaning that we've computed the dp values for this entire prefix. We know they're right because that's how dp works. Then now we consider on tacking in this value. Say we're going to jump from somewhere to here. Right? Now, if we do that, because again, like the basic idea of the way powers of 2 work, it doesn't matter where we came from previously. Because the absolute difference of any two elements on this range is at most 2 to the 2 minus 2 to the 0, which is 2 to the 2 minus 1. But here, we have 2 to the 3. So the smallest possible difference we can get is this. 2 to the 3 minus 2 to the 2 is equal to the 2 to the 2. So the minimum difference we could ever get from a jump from somewhere on here to this one is larger than the maximum difference we can ever get from any jump within this prefix. So it doesn't matter what previous jump we did. We can always make the jump to here, provided that the tags are the same. So that's the first idea. That when we consider tacking on this value and considering it, first, we don't care about j from the previous ones we do. And so now the rest of the idea is that we don't care about j at all. And the reason is that, now say we're going to jump from here to here. Note that again, because of the way this works, when we're storing this state, we don't care that we came from here, because sort of as I've said before, our next jump is forced to be on a greater value. So the next jump we make is not going to care about the complexity of this jump, the difference between the blue values. So we don't care about it because the next jump doesn't care about it. So really in either case, if we do the dp transitions where we do sort of both jumps at the same time, I don't know why I started using this color. Basically we can cut out this factor. And so basically, now the only thing we care about is that the previous jump ended at I. Now this makes n memory, and it's still n cubed because the transitions aren't the greatest, because here, jumping to here, it's simply, we can pick anywhere that has a different tag, so that's fine, that's an OVN transition. But here, we have to consider coming from any previous value that's smaller than, that has a smaller distance here. That's the only way the complexity would work. Like if we come from here, then we can jump from any value from this prefix. And if we're going to here, then we can jump from any value on this range. But the idea is that, say we compute it for this one, then we compute it for this one, then we compute it for this one. Then first we're interested in coming from this interval, which is nothing. Then we're interested in coming from this interval, then we're interested in coming from this interval. So we can keep a running maximum of the possibility from jumping from here and then to a later one. And then now when we jump from here to here, then we can consider only that running maximum, and then we can make these jumps. I guess that makes sense? Yeah. And again, only if the tags are different. Then that allows us to compute the new values for dp for every other location. And so this is sort of the transition where we force to use this, because if we don't use this, then it's fine, because we already know that we computed the correct dp values for this prefix not using this value. So really the only other way we can improve the dp values is by forcing ourselves to use this jump. And we do. That's what we consider. These are the transitions we make. We make transitions where we're using this index in the array. And then once we process this, then we continue on. We go to the next index. We do the same thing. So now because it's a running maximum, it's only n squared. So n squared time of n memory. In code, it looks like this. We say, for example, read in the things. Then for each index from the beginning to the end, then we keep a running maximum moving to the left. We basically consider first the transition from jumping from here to here, and then we consider the transition from the running maximum covers this interval. So then we go from like anywhere jumping from this interval to here, and then from this position to this index. Of course, only if the tags are not the same. And the answer is like the maximum over any value of dp at any point in time. So really, it's sort of like it's a bit like Floyd-Warshall if you think about it. It's basically like dp of I and j is equal to the maximum score for ending at I, and the largest used is j. Except because we process the values in like increasing order of largest used, we can cut out this dimension in memory. Because we're iterating from j from 0 to 1 to n minus 1. So that's the idea. It boils down to like the standard like the memory optimization trick for dp. It's just sort of a bit more hidden in the way that it works. Okay, this problem E1 is way easier than I thought it was. So basically the idea is you have an array, you want to divide it into segments such that within a segment you cannot choose two numbers, for example x and y, such that x times y is a perfect square. Now this is a concept that comes up a lot within number theory, and this becomes easier if we break the numbers into their prime factor representations. So for example, say x is equal to like 2 to the 7th times 3 to the 5 times 7 to the 6th times 17 to the 5th, and then y is equal to 5 to the 9th times 11 to the 8th times 17 to the 3rd. Now a number is a perfect square if and only if all of its prime factors, all of the powers on its prime factors are even, right? Because say it wasn't. Like for example, say we had like z is equal to 2 to the 3rd. Actually, say it is first of all. So we have like 2 to the 2 times 3 to the 4th times 5 to the 10th, for example, right? Then we could divide these by 2 because they're powers and then split them up into two numbers. So we can specifically say, look, this is 2 to the 1 times 2 to the 1, where we divide these by 2. This is 3 to the 2 times 3 to the 2. And this is 5 to the 5 times 5 to the 5. So really, this number is equal to 2 to the 1 times 3 to the 2 times 5 to the 5 squared. And yeah, so if these prime powers are even, then, or if the prime exponents are even, then it's a perfect square. And if it's not, say we had, for example, 2 to the 3 instead, then like what do we do, right? There's no way to divide it evenly so that such that like x plus y equals 3 and both x and y are even. That's not possible. One of x or y have to be odd, and then they're not equal, so we can't break it into a perfect square. And we can't represent it as a perfect square. So really, a number is a perfect square if and only if all of its prime exponents are even. And if some number doesn't exist, for example, like z can also be represented as 2 to the 3, for example, times 3 to the 4 times 5 to the 10 times 7 to the 0. And then that's fine because we don't really care about this at all. Because A, it's even, B, it's not even there, right? So we just ignore it. But 0 is even, so it ends up being nice anyway. So what does this mean for the numbers x and y? Well, x times y is a perfect square if and only if, again, these things are even. Or if all of these things are even, right? So another way to think about evenness is saying that like a is even if and only if a mod 2 is equal to 0. Right? So now we can consider these things modulo 2. So we don't care about these exact things, we only care about these powers modulo 2. So we can change every number. For example, x becomes into the prime powers mod 2. So it's 2 to the 7 mod 2 times 3 to the 5 mod 2, 5 mod 2 times 7. This is a bit ridiculous the way I'm writing this out, but yeah, it'll get there. Times 17 to the 5 mod 2. Whoa, okay, that was not intended. Right? So then this is equal to 2 to the 1 times 3 to the 1 times 7 to the 0 times 17 to the 1. And this is 0, so we can really just get rid of it. 2 to the 1 times 3 to the 1 times 17 to the 1. And because we know all these powers are going to be 1, it's simply 2 times 3 times 17. We do the same thing here. Y is equal to 5 to the 1 times 11 to the 0 times 17 to the 1 is equal to 5 times 17. Now the claim is that the number is a perfect square only if, like if and only if, the change we make where we take all the prime powers mod 2, like these new numbers are exactly the same. That's the only way it's possible. Because if that's not the case, then some number is present in this one that isn't in this one, or vice versa. And that means that this has a power of 1, so it can't be a perfect square. If they're different, then some number is present in one of them but not in the other one, and that means that it has a power, and that means that it has 1 mod 2, so that's not valid. But if they're the same, then everything cancels out with everything else. So for example, the 17 cancels out with the 17, so the remaining number we get is 2 times 3 times 5 times 17 squared, but this is a perfect square, so we kill it, so we get 2 times 3 times 5. So only if these representations of x and y are the same do they form a perfect square when they're a product. Right? So now we basically need to make it so we have a new array, and in fact I think we can just, these numbers aren't that large, so we can do this however we want. Basically we have a new array, we need to break into segments such that we have no duplicates in any segment. And I'm fairly sure you can just straight up greedy this, so I think that's basically it. Let's see, any FSTs? Cool. Yeah, I'm like quite sure you can just greedy this, so should be fine. Like basically you just you go through the array, you stick everything in the current segment until you hit a duplicate, and then here you're forced to start a new segment, so you just keep going until you hit the end. So for E1, basically, after you do all this number theory stuff and understand how that works, it's just greedy. Right. I think the way to prove that is just like saying like suppose you didn't, right? Suppose that like what you did wasn't like suppose that what you did wasn't suppose the greedy wasn't optimal. Then like there's some other segment that there's some other partition that uses like a different set of segments. Um yeah. It's sort of like contradiction-y. Then like suppose okay, do you I guess I'll prove this because I have nothing better to do. Suppose there's some optimal partition that's different from the greedy. Then consider the first point where they differ. Because the greedy stops at every point where we're forced to split, like where we have a duplicate, the optimal partition here is going to have a smaller interval than the greedy. But then this doesn't coincide with anything in this previous interval, so we might as well include it. So we can extend this interval until it's the same as the greedy, and then now we're forced to make a difference here, so now we have the same thing as the greedy again. So we continue this argument and we can prove that every interval, assuming that everything else before it is the same, then this interval also has to be the same. So it's like induction, kind of, the way it works, the way you can prove it. So you can prove by induction, I guess, that if there's an optimal partition that's different from the greedy, then you can convert it to an optimal partition that's the same as the greedy with the same answer. So it's still optimal. So I think, yeah, greedy should work. Anyway, what I did was not that. I did some complicated segment tree DP with binary search on a sparse table. So really don't do that. Don't read this. Just do the greedy. It's simple. Like this code is all you really need for the greedy part. This code right here. Everything beyond this is garbage. Like, don't do this. This is building a sparse table. This is doing some segment tree DP. I'm doing binary search here to find like some. It's just so messy. And in fact, it might be arguable that this binary searching approach extends to E2. And in fact, I think it does, but you get a complexity of O of n times k squared times log of n, which is basically no better than n squared. So there is no reason to ever want to do that. But there is a better way we can do it. Okay, so for E2, what we can do is we can say k times, we can pick some element and modify it, at most k times. Right, okay, so we only have a problem if these values are identical for two values. So assume we have this new array, this new like compressed array of prime factors. So these are also called like square free numbers, I think, that no perfect square divides them. So we have, for example, these square free numbers. So we have 30, 6, 10, 15, 2, something like that. Now say none of these are equal, but say we had like another 10 here, right? So then we want to remove this 10 with one of our operations to make it so now we can use this whole array, right? So we can basically just change it to any number that's like not already in the array. Right? Like let's, for example, pick the largest prime that hasn't been used. Let's make it 7. 7 has not been used as a prime. So say we want to remove another element now. We can make it a different largest prime that hasn't been used. So for example, 11. So we can always pick a number that's not the same as any of the other numbers. So really when we say we're doing an operation, it's more like removing an element. We're just going to say get rid of this because we can always make it obsolete. So with that in mind, we can let dp of I and j be the answer for the prefix like 0 to I, switching my indexing up here with j operations done. Now the basic idea here is when some element is a duplicate, like when some element is a problem and that having both these elements in an array would cause a problem, then it's always a duplicate. It will never stop being a duplicate. Because like if we sweep the prefix we're solving for to the right, then this is always going to be a duplicate. So as we go along, we can maintain like a set of the duplicates that we currently have. So for example, something like 2, 15, 10, 6, right? So as we go along, what we can do is we can maintain this set. So let's say, for example, we're going to move this down, just so I can have some space. And so we have this open set. Currently, we're here. This is not a duplicate with anything, so we move on. Now we're here, not a duplicate with anything. Now we're here, now we're here, now we're here, now we're here. We've seen a 10 before at this position. So now we need to say that this position is now in our set. So now we've seen a 2 before in this position, so we need to say that 4 is now in our set. We've seen a 15 before at this position, which is 3, so now this needs to be in our set. We want them to be ordered just because that makes it easier. So we can do that. Okay, you know what? Easier to just... Yep. So now, here, now this 10 becomes a duplicate. But this 10 is still a duplicate because if we did one operation to remove, say, this one, then this would be a problem. Then this wouldn't be a problem, but this would cause a problem with the previous 10. So some element is always going to be a duplicate. So now this 10 at position 5 is a problem. And then when we're at 6, this 6 at position 1 is a duplicate. So now we can go here, and we can close off the set. So as we go along, we can maintain the set of duplicates just by like, if this is previously seen, then insert its previous index into the array, into the set, and then now we have this as the previously seen index. Yeah, so again, you can assume these are like compressed numbers. What I did was I just made this like a list of the actual numbers, like for example 2, 3, and 5. And then you can have like a map that maps lists to indices, and then it would work that way. Like 2, 5, this would be 3, 5, this would be 2. If you had 1, then it would just be an empty list. Right, and then this is also 2, 5. So these match, so they're the same. And the lists are at most like log n, log 2 of n, log base 2 of n, or log base 2 of the array values, because that's how many distinct prime factors you can have. So it's not that bad. It's like, maybe it's like log squared of n or something. Log squared of ai times n inside the complexity or something. Some sort of log squared, but it's not that bad really. I think vector comparison is not the slowest. I hope. Should not FST get TLE or whatever. Hopefully not. So now the basic idea is, say we're, for example, at this 6. So we know we have a duplicate. We know we have a duplicate here, 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 and here. Because this is going to be a duplicate for this 10, even if it's not a duplicate for the 6. So if we do 0 operations, we can have this be a partition. And because the greedy works, these DP values are going to be monotonic as you go to the right. So for example, like dp of I minus 1 for some j is always less than or equal to dp of I for that j. Because like this is the same prefix as this, but you add an extra element here. So it's only going to be harder to do this one. It's only going to take either the same or more partitions to do it. More subarrays. Right. So now, if we do 0 operations, the best we can do is here. So we basically just rely on the dp value for this prefix now. And that's our answer for doing no operations. If we're here, if we do a single operation and we remove this one, then now the prefix we get is this, or the suffix we get is this. If we do another operation and we remove this one, then the suffix we get is this. And in particular, the suffix we get for removing something is whatever index the previous duplicate was plus 1. So this would give us the prefix of, like, for example, 6 to whatever our current prefix is, I. And this would give us 5 to I. So we can basically just iterate through the k largest elements of this set, and update our DP values accordingly. And also, it may help for implementation. What I did was I just stuck like a sentinel value, a -1 here. So that way this would consider the case of using the whole prefix, or using like the entire thing as one operation. If we have no duplicates, then this would be the largest element of the set. If we have one duplicate, for example, here, then we remove it. Then again, we have just the entire prefix, which is exactly 1. So it just helps with implementation. Because note that it corresponds to being able to use the prefix of 0 to I. So then we would rely on DP of like -1, which we can just say for convenience is 0. Right, so that's the basic idea. We go through the k largest elements in the set, and we update the DP values accordingly. Now, a bit more care, I guess, is required to make this not k cubed. But you can also notice that DP of I minus... We know that DP is monotonic in terms of indices. But it's also monotonic in terms of operations. If you use more operations, because each operation removes an element, it gives you a lower cost or the same cost each time. So we also know that DP of I minus 1 j is always less than or equal to using... Alright, this should be like DP of I and j is always at least as good as using fewer operations. So to do that, what I do is basically like, say you're solving for DP of like, what index is this? 1, 2, 3, 4, 5, 6. Wait, 1, 0, 3, 6, 9. So DP of 9 and, for example, like 3 operations. Then if we're using this prefix where we remove 2 things, then it basically relies on the transition of DP of 3 and 3 minus 2 plus 1. You may also think that it may, for example, use fewer operations, so for example 3 minus 3, but it's not necessary because this is less than or equal to this. This is better than this, so we only have to consider this one. And similarly, we don't have to consider future indices because now we know that this is, for example, going to be like this. Using a smaller index is better than a larger one, which is not something I realized when I did my segment tree. So yeah. So really, we only need to consider one previous DP value for the transition. And then I just did this extra thing where I set, like, I just ensure this is true by setting DP of I, j to the minimum of itself and that of using fewer operations. I'm not sure if this is necessary, but it just sort of helped. Because it doesn't hurt the answer. It's not going to change it for the worse in any way. Like, it's not going to make it so you use more operations. So I just did this at the end of every, for each I. And it just sort of helped. And then the answer is dp of m minus 1 and k. It might help the 1 index just to like get it, like be able to think about the dp and visualize it. If that's the case, go ahead. It just depends on what you want or how you think of things. So I think this took me longer to explain than it did to solve, which is interesting. But yeah, monotonicity is cool. There's so much stuff you can do with it. So like this is nice. So really this is, so we consider at most k possible different suffixes of the array to take as our current interval. So this is k. And then we have to consider every possible We have to consider every possible number of operations that we've used beforehand. So this is another k. So for each I, we use k squared. And for the indices, inserting into a set is log of n, but iterating is O of 1 per like move, or per iteration. So it's like something like O of n times log of n plus k squared, which is fine. It's not that bad. In fact, it barely even changes my runtime compared to E1. So it should be pretty fine. I think most of the hard part is the factorization anyway, which you can find in my template if you want, or you probably have it written if you're interested in solving this problem. So yeah. There's also like maybe a squared or something because of my inefficient like working with map of vectors, and vectors have like size of log. It doesn't matter. It really doesn't matter. Yeah. So basically it's nice. It works. So we got E1, we got D, and I guess that settles everything. So hope that works. I need to like, I hope my facecam wasn't blocking too much. If it was, I'm sorry. I need to get used to that. Hopefully not. I don't know, I guess we'll see. If something's like blocked, you can just ask me in the comments about it or something. But yeah. I may have to make a screencast for fewer problems for the education round, just because like daylight saving shifts the time, so I have less time to do a particular round. So it sort of works that way. Yeah, I guess we'll see. I don't have much more to say. So hope you enjoyed the round. Hope you enjoyed it even though it was unrated. But yeah, that's all I got. So see ya.